Record. And we're off. So, we have talked about the regulation of the heart and cardiac output. And cardiac output does affect blood pressure. So, the harder the heart is pumping and working, the more forcefully the left ventricle is going to eject blood, which means that arterial blood pressure is going to increase. So those two things are proportional to each other. Cardiac output is proportional to arterial pressure. And of course, this is under neural regulation as well as having its own intrinsic conducting system. So we have this sort of peace sign shaped relationship where arterial blood pressure is partially due to cardiac output, but it's also partially due to something called resistance, which we'll discuss. And then this is another piece that we're going to spend a lot of time talking about today. Let me grab my laser. There we go. Pretend laser. So capillary pressure and capillary exchange this is kind of the goal. So this leg of the loop is the delivery system, and it has its own dominating forces and set of challenges. And then this part is the goal. So you want to be able to exchange things with your cells and tissues. So have those cells and tissues be able to carry wastes away and provide those cells and tissues with nutrients and oxygen primarily, as well as other things like hormones, stem cells, cell signals, etc. So after that, we have venous pressure, which is quite a bit lower than arterial, and importantly, venous return to the heart, which starts everything over again. So we're going to address pieces of all of this for the next portion of the presentation. So blood flow is exactly what it sounds like. So remember from the blood portion in the blood chapter, when we talked about the characteristics of blood, what we talked about was how it's slightly viscous, so it's more viscous than water, and viscosity is resistance to flow. So like, maple syrup and molasses are a lot more viscous than water, for example. So that's one factor that influences blood flow is blood's viscosity. The ultimate cause of its flow is pressure differences. So fortunately, this is pretty easy to understand, even though the symbol for it looks scary. So like, oh no, a triangle, it just means change in. You guys know change in, delta. So delta P just means pressure 1 minus pressure 2. The bigger that difference is, the faster the flow. It obeys the same rules as diffusion. So, in diffusion, particles diffuse down their concentration gradient. In blood flow, blood flows down its pressure gradient. So from an area of high pressure, aka the heart, to an area of low pressure, aka the capillary beds and venous system. So the biggest thing to deal with and think about here is other factors influencing resistance. So in addition to the viscosity of blood, what forces in the arteries are going to oppose the work that the left ventricle is trying to do? Why does that left ventricle wall have to be so much thicker than the right? Is kind of the question we're answering. So flow is proportional to however steep the pressure gradient is divided by the resistance. So let's take a moment without numbers to look at this equation for a moment. Delta P is a subtraction function. So it's the first pressure minus the second pressure. So the bigger delta P is, the greater the flow, right? Because if we make the numerator larger and hold the denominator steady, we're going to make this number increase. If we hold the pressure differential steady and we increase resistance, we're going to make this fraction smaller, and that's going to slow down flow. So for the most part, delta P remains relatively stable, and that's of course because there's only so much pressure your left ventricle is really capable of generating. And assuming you're in a normal body posture and not moving at a weird speed, like, sitting or standing, the pressure difference between your heart and your veins should be relatively stable. So resistance is really what we're worrying about. So as I mentioned, if delta P increases, flow increases. If resistance increases, flow decreases. Okay, so on this bottom chart here, we just have blood pressure on average. So this is averaging across many vessels, ranging from arteries that are pretty close to the heart to veins that are quite far away. So arterial pressure ranges from about 100 to about 35 millimeters of mercury. So down here. Capillary hydrostatic pressure is that measurement between about 35 and 18, so this purple area, and venous pressure is 18 to 0. So when I say occasionally, and I think I've said this before, veins are functionally a zero pressure system, this is what I mean. So they're not subject to much pressure at all. The pressure, in fact, dissipates very, very quickly after leaving the capillary bed. So the pressure in a large vein, excuse me, my voice cracked. The pressure in a large vein, like for example, the hepatic portal vein, is going to be 0. Or it should be anyway. I'll also talk about what happens when it's not. So peripheral resistance, I've actually already mentioned this, and that is due to the fact that we talked about the left ventricle and it needing to be beefier to overcome peripheral resistance. So I've mentioned this before in passing, but now I'm going to really tell you what it means. So we know that resistance opposes blood flow, and we've talked about viscosity. We haven't talked about vascular resistance, and that's kind of the biggest piece of the puzzle. So to understand this, and this is actually, interestingly, this is an exercise that we are asked to do in new faculty orientation. So new faculty orientation is this like big, long day of some varying activities, some of them more useful than others, let's say. But one of the ones that really stuck with me was one about, basically it was about like varying challenges to completion of tasks that students have. And for one of them, we were asked to breathe through a straw while trying to fill out like a medical intake form, you know, the one where you go to the doctor and you're like, I'm this many years old and here's how much I weigh, and no, I don't smoke and I don't have a history of blah disease in my family, like one of those. So we were handed one of these and we had to do it while breathing through a little tiny straw. And I thought when I got the straw, I was like, no big, I can totally do this. And it very quickly became really, really difficult to both concentrate on the task I was doing and try to not die because the resistance from breathing through that little straw was so high. And the same kind of thing applies to your arterial system. So your arteries are pretty big close to the heart. So your aorta is quite large in diameter, for example. But the further you get away from the heart, the smaller those tubes are. So you have the same amount of fluid being crammed into a series of narrower and narrower tubes, which creates a lot of resistance to flow. So one component of the vascular resistance is length. The longer the tube is, the more friction there will be between the fluid in the tube and the tube walls, and then diameter as well. So if you have a large diameter tube, there's going to be a lot of fluid in that tube that's like in the middle and therefore not in contact with the walls and not rubbing up against the walls and creating friction. In a smaller diameter tube, more of the fluid is going to be rubbing up against the edge and being slowed down by friction. If you combine that with viscosity, so resistance to flow of the fluid itself, and turbulence, which is flow that is not in a straight line, R becomes really big the further away from the heart you get in the arterial system. Due to the, I realize my imaginary YouTube audience can't see the question. So the question was, how does flow stay constant through the whole system? And the answer is the heart. So that's why it's so dangerous if the heart stops, because the heart is the mover and shaker and initiator of the pressure gradient that drives the flow. So for example, just to give you a comparison, vertebrates have this system where we have a heart, and it generates a considerable amount of force, and then we have these closed tubes that everything flows through. So we rely on a pump to move our blood around whether or not we ourselves are in motion. That's how we work. As long as the question, just to give everybody insight into what's happening in the chat, the question is saying, but with all the different sizes of vessels would change that. It changes for the individual vessel, but as long as the left ventricle generates sufficient pressure, it doesn't matter. It's enough to sustain life. And the answer also is that the exact flow rate is not constant for every tube in the body. They do vary with pressure. So as long as we've got venous return and the left ventricle generating about 100 millimeters of mercury of pressure, we're good. The comparison I was making was really about, we do it that way. There are other creatures that have an open circulatory system, which means that instead of being in tubes, their blood just kind of sloshes around, which takes care of the resistance problem, but then there's no pressure gradient really either. So these critters have to sort of be in constant motion in order for their blood to slosh around enough to be effective in delivering oxygen. So although our closed circulatory system presents some challenges, so does an open one. So there's no perfect way to do this. We just have our way that we do it. All right. So total vessel length is a lot. So if you think about the aorta and all of its branches, and then all of those branches, and so on and so forth. So take a mental picture of all the vessels that you learned for the first part of Practical 2. And then keep in mind that I made you learn a very small subset of all possible blood vessels. So there's tons of them. That's a lot of length, which means a lot of friction. So resistance is proportional to length, which means that the longer a vessel is, the higher the resistance. So if you use really simple numbers here, we're just going to use unitless numbers. That's easier, and pay attention to the rules for calculating surface area of the inside of a tube. So that's what we're doing. So don't worry about the units of these. They don't matter. The relative proportions do. So if you have a tube with an internal surface area of 1, the flow is 1 and the resistance is 1. So this is our reference tube. If the internal surface area is 2, so you have more surface area, which means more resistance, by our equation, the flow is cut down to half. And that's just because this longer tube creates more opportunities for friction between the fluid flowing in there and the walls. So this is a reason medically why weight gain, not minor weight gain, everybody has minor weight fluctuations, I'm talking about significant gain in specifically adipose tissue. Weight gain results in increased vasculature. So one thing that no one ever tells you about gaining adipose tissue is that adipose tissue releases something called angiogenesis factors, which are factors that encourage growth of new blood vessels. So your fat recruits blood vessels, which means that the more subcutaneous fat and visceral fat you're storing, the more tubing you now have, because that fat needs blood supply. So with weight gain, you get an increase in length. With length, you get an increase in resistance, and resistance increases the afterload on the heart. So remember from the heart chapter, we talked about afterload, and we talked about it on terms of the resistance that the left ventricle has to overcome, which means what pressure must it generate to open the aortic valve. The higher that is, the harder the left ventricle has to work. So the medical link between weight gain and blood pressure, and the reason why if you're suffering from chronically high blood pressure as an adult, one thing that your clinician might do is say, hey, you should consider losing some weight, is to try and get rid of that extra tubing to release you from some of those powers of resistance. That's not the only cause of increase in blood pressure. There are many others. That's just one. There's a question, and that is the vessel stretching or growing. Growing. So angiogenesis factors encourage mitosis and the creation of new blood vessels. All right, so vessel diameter. This is perhaps the largest influencer of vascular resistance because it affects resistance the most quickly. So with very small changes in radius, you get pretty big changes in resistance. So if we look here, and I might actually go and get my, hello, where's my cursor? There it is. I want to zoom in right there. Okay, so this picture looks pretty simple, but there's some additional stuff going on. So what you're looking at is a longitudinal section of a tube, and then a bunch of arrows. So the arrows are indicating the direction of flow, and their thickness is analogous to how fast the flow is. So remember, any fluid is made of molecules, right? And these are gonna run into each other and run into stuff. Also, in fluid dynamics, we call this straight flow laminar flow. So laminar flow is the fastest kind of flow. So this is actually an idealized situation. We're assuming that all of the flow in this tube is going to be laminar always. That's not actually the case, but for this exercise, we're going to assume that. So notice the arrows in the center are the largest, and the arrows get increasingly small as you approach the wall of the tube. That's because not only are these particles running into each other at higher rates as you approach the wall of the tube, because there's a boundary and they can't move out of each other's way, they're also running into the edge of the tube itself. So what that means is if you were to look at, let's say you have a tube with zero flow, and you pick a line of particles in the tube, and then you start the flow. Those particles are going to spread out into a dome, where the ones in the center are going to be going faster than the ones on the edge. So flow in tubes is actually domed or convex, not straight. There's a lot of drag on the edges here. However, the bigger your tube is, the fewer particles there are in contact with the wall. Okay, so let's examine some numbers here. So now we're changing radius and diameter. And to do this, I'm going to show you this number first, and then we're going to flesh it out with equations. So here we have a 2 centimeter diameter piece of tubing, and down here we have a 1 centimeter diameter. So we've cut the diameter in half. So in 2 centimeters of diameter, the resistance to flow is 1. If you cut that in half, the resistance increases 16-fold. So relatively small change in diameter, many-fold change in resistance. That's why this is the biggest contributor to issues. Why is that? Well, here is the calculated resistance fraction, and that is resistance is proportional to, notice that this is proportional to, not equal to, so there's other stuff that factors in here. It's a proportion. So resistance is proportional to 1 over the 4th power of the radius. So if I make the radius be smaller, I raise it to the 4th power, and then I put a 1 on top of that, that's going to create a very high amount of resistance. So, as you can see, the outcome of that is if the radius decreases by half, resistance increases 16-fold. So, by a lot. And the converse is true as well. So if the radius increases by 2, you get a significant relief of resistance as well. Okay, so that was vessel diameter. We also have other contributors to resistance. And one of those is viscosity. So your hematocrit does determine this. So to give you an idea, in some bleeding disorders, thinness and thickness of blood does matter. So hematocrit does play a role. So you would expect to see, for example, decreased viscosity in someone with types of anemia. But more commonly, viscosity of blood is affected by the concentration of plasma proteins. So to what extent the liver is effectively producing fibrinogen, albumins, and other proteins. The other component is turbulence. So one of the things that creates turbulence in your vasculature is forks in the road. So for example, like where your common carotid branches into your internal and external, at that fork, there's going to be a little bit of turbulence because the flow has to split, right? So it's going to run into that middle forked wall and then go in one or the other direction. So that creates a little bit of turbulence. The other cause from a clinical perspective is, of course, plaque. So arterial plaques are going to be fatty deposits that build up on the inside of the arteries. So here's a really bad one. And not only do these make the diameter of the vessel smaller, which dramatically increases resistance, but they also make the flow turbulent, which further increases resistance. So arterial plaques are bad for two reasons. So this one is an H&E stain of one. So this is a histology image. And then over here, we have a cross-section of a fresh one. This is the same coronary artery, not identical to this one, but it's the same artery in general anatomically. And you can see that there's this complicated plaque inside of the wall. All right. So arterial blood pressure is dynamic. What I mean by that is, think about the pressure being generated by the left ventricle, and think about how it changes versus systole versus diastole. So in systole, the pressure is very high. And if you think about blood pressure, your systolic over diastolic is usually about 120 over 80. So that means that in the vessels that are close to the heart, we're going to have these staggering highs of 120 millimeters of mercury and then these lows of 80 as the heart changes pressure. So this gets less and less true the further you get away from the heart. But what this means is the pressure in your arteries obeys this sawtooth waveform. So it goes up and down a lot. So, at one moment, one of them might be 120, and then it goes down to 80, and then back to 120, which means that getting a meaningful number out of arterial blood pressure is going to require that you do something to normalize those numbers, so they're not vacillating wildly between two. So mean arterial pressure is that pressure. So mean, meaning average, and you can see that it kind of splits the difference. So it follows the curve of the two delimiting lines. So it reflects the pressure, but it's not identical to this sawtooth waveform. So it's a way to estimate what the average pressure in arteries is, which is a much more useful number clinically than all of this sawtooth business up here. Also, note pulse pressure. So pulse pressure is just the difference between systolic blood pressure and diastolic blood pressure. That's all. So it's just subtraction. So if I ask you to calculate the pulse pressure, I would give you the systolic and diastolic blood pressures, and you would just have to subtract them. That's it. So that's pretty easy. Okay. So mean arterial pressure, or MAP. So this is the equation, and it's just pulse pressure divided by 3 plus diastolic. So let's say blood pressure is 140 over 90. First, so this is the only thing you need to calculate MAP. So if I give you the blood pressure, you can calculate the pulse pressure from that and then put that pulse pressure over 3 and then take the diastolic pressure and plug it in. So this term right here, this blood pressure reporting, is the only set of numbers you need to do all of this math. So diastolic plus the pulse pressure, which is the difference between these two, which is 50 over 3, ultimately equals 170 millimeters of mercury. So as long as you remember this equation, if I give you a blood pressure as it would be reported in the doctor's office, you should be easily able to calculate mean arterial pressure. Does anybody have any questions on this before we move on? Alrighty, let's keep going then. Tiki is driving me nuts today. She is over in her cage, like racing around. She's doing squirrel NASCAR. Okay, so let's do one more example before I move on. So 120 over 80, which is a more normal blood pressure. So this is kind of what you're shooting for blood pressure management. 140 over 90 is a little bit high. You can see that for a relatively small change in reported blood pressure, you get a pretty big change in mean arterial pressure. So this pressure is important because this pressure is going to tell you about how much afterload the heart is dealing with when it comes to cardiodynamics. So certain kinds of heart disease that result from, for example, chronic high blood pressure are a result of the heart dealing with high afterload over a long period of time. So for example, you get left ventricular hypertrophy, which is a really, really high pressure in the left ventricle that causes the left ventricle myocardium to get really buff. And it might seem like having a really swole heart is good, but it's not. So the thicker the wall of the left ventricle is, the less good it is at filling, which means that it can't work as efficiently. And that also creates afterload. So this number here, this mean arterial pressure, is a really useful indicator to sort of function as an analog for how hard the heart is having to work to overcome afterload. Okay, venous return. Arteries get a lot of attention because they have some sexy math associated with them. And of course, you know, that's where we measure blood pressure by compressing the brachial artery and blah, blah, blah. But I feel like veins are really cool. Here's the cool thing about them. Oh, someone's asking if someone's heart swells, can it return to normal size eventually? Yeah, the answer is yes. So that's actually a really good question. And it gets me, it gives me an opportunity to address one of the Snapchat review questions that I posted. So let's do both. Thank you for that excellent question. So for YouTube folks, the question was, if someone's heart swells, can it return to normal size? So in the event of left ventricular hypertrophy, is that reversible if they undertake the lifestyle changes to bring their mean arterial pressure down and, you know, maybe reduce vascular plaque, etc.? And the answer is yeah, it can. So hypertrophy is tissue growth by an increase in cell size, not an increase in cell number. And what that means is the heart muscle obeys the same principle as your skeletal muscle. So like, I'll use myself as an example. My gym's closed and I've been working a lot. So all of the effort I put in previously to hypertrophy my muscles by going to the gym and lifting weights is now gone because I haven't been consistently subjecting my muscles to those forces. So formerly my skeletal muscles had hypertrophied to some extent because I was using them more, but now that they're kind of in disuse, my impressive muscles are gone. And the same thing applies to heart. So if your heart's constantly working really, really hard, it's going to hypertrophy and those cardiomyocytes are going to get bigger by adding more sarcomeres. But if the afterload pressure is gone, the cardiomyocytes will shrink back up. So it's totally possible to reverse. It's just that normally people are unwilling to change their behavior enough to have an effective change in their heart size. So that's talking about hypertrophy specifically. However, it doesn't address other kinds of heart size change. So certain other kinds, like not the one I'm talking about, result in like a large, weak-walled, baggy heart. And that is not especially reversible. So thank you for that excellent question. All right, so here's why veins are cool. You don't have little feet hearts to pump your blood back up from your feet. So if you stand up, I'm not going to do it right now, but if you stand up and think about how much distance there is between your toes and your heart, it's more than half of your body height, right? It's pretty tall. And if you're standing, that means that gravity is pushing that venous blood away from your heart. So how the hell does it get back up there? Well, the answer is skeletal muscle pump, respiratory pump, and valves. All of these things working together are good enough to keep blood steadily returning to your heart in an amount that is life-preserving, which is kind of amazing. Because we think of the heart as being this big pump, and it's very important because it's pumping the blood out. But we don't have a pump at the other end of the system, and yet blood returns to the heart just fine. So the muscular compression is just your skeletal muscles squish your veins. And when they do that, blood squishes back up through the valves in your veins and then falls back down, closing the valve cusp. So blood sort of inches back up from your periphery. The respiratory pump is perhaps cooler. So the respiratory pump is basically when you take a breath in, I'm doing it right now, you're making the pressure in your thorax lower, and that draws all the blood in your abdomen and in your thorax up the veins in there. So it works on the same principle as using a straw. So when you use a straw, you stick a tube in some liquid, and then you make the pressure in your mouth lower than the pressure in the tube, and up the liquid goes. Same deal with your vasculature. So the respiratory pump is really important. So what that means is just the simple act of breathing helps venous return. And venous return is important because it influences stroke volume. How? Well, your heart can only pump out as much as it receives. So if you see a decrease in venous return, stroke volume is also going to decrease. If you see a decrease in venous return, cardiac output, because it's a function of stroke volume, will also decrease. And venous return influences blood pressure as well, because the more blood that's backed up into your venous system, the lower your blood pressure coming out of your heart will be. Okay, so this is the piece of blood vessels that tends to cause the most anxiety for students. And I'm not saying that to increase your anxiety, but rather to say it's totally achievable. You just have to think about it piece by piece. So trying to sort of ramjet all this information into your brain all at once and instantly understand it is going to make you feel anxiety. I know it did for me. But it's really doable if you just go piece by piece. So that's what I'm going to do. So we have blood arriving at the capillary bed through these little arterioles. And depending on how big the capillary bed is, it takes between 1 and 3 seconds for it to pass through. So this is just kind of a reference one. They can be quite large or quite small. It really varies depending on the size and metabolic demand of the organ or tissue. And then during that 1 to 3 seconds, this is pretty fast, we drop oxygen off at the tissue, we pick up CO2 from it, hopefully drop some ions and nutrients off, pick up other wastes, and drop off or pick up hormones. So there's a lot of trading back and forth happening in those 1 to 3 seconds. So that seems relatively straightforward, but I want to actually, let me go back one. This exchange right here is the whole point of both breathing and of having a heart. So this is the sort of end point that all of those pumping and breathing and inspiration and expiration, this is the end point that the goal is. So if your heart stops, this stops. Or if you stop breathing, this stops. And that's what ends life. So this is really important to understand because this is the life-sustaining end point of both breathing and of pumping your blood. Also, if stuff goes wrong with that, bad stuff happens really quickly, and I'll explain that as well. Okay, So fortunately, the means of capillary exchange are at least somewhat familiar to you because you guys have all had 160, so you understand diffusion really well. Particles move from areas of high concentration to areas of low concentration. That's easy to understand. Less easy is filtration and reabsorption. So these two are going to take a little bit more explanation. So diffusion rates are maximized when the diffusion distance is short and the concentration distance is long. Or excuse me, concentration distance is large. I meant gradient, sorry. Not enough coffee this morning. So short diffusion distance, large concentration gradient. I'll show you the math of that as well. Also, even if you have a really short diffusion distance and a large concentration gradient, if the molecule being diffused is too large, that's going to slow it down. So imagine trying to get like large sized particles through a colander. You'd have a hard time, right? So small molecules like water and ions diffuse the fastest. Larger things don't tend to go by simple diffusion. They need transport help. So if you watched the previous videos for this, you'll note that we talked about continuous capillaries versus fenestrated capillaries versus sinusoids. We're going to be talking about primarily continuous capillaries for the next few slides because that's most of your capillaries. So the diffusion really happens by substances squeezing between endothelial cells or sometimes through pores. So we've got water, small ions, and small organics. There's also membrane channels for ions. So these are going to be, of course, things like sodium channels, potassium channels, and sometimes exchange pumps as well. And then anything that's lipid soluble can, of course, just move straight through the lipids, right? So like steroid-based hormones can do this. Lipid soluble vitamins are another example. Okay. So now I'm going to pause here and explain what I mean by hydrostatic pressure. So hydrostatic pressure and osmotic pressure are very, very different. They are both driving forces for movement, but they obey very different principles. So the easiest way to understand hydrostatic pressure is just think about a hose. Hydrostatic pressure in a hose is just when you turn on the spigot at your house to let water into the hose. If you have one of those garden hose sort of spray nozzles on the end of your hose, you create a closed system with high pressure inside of it. So the water is entering the hose, but it can't get out unless you let it out through that nozzle, and that's what creates the pressure coming out of the nozzle. So hydrostatic pressure is just the pressure of a fluid pushing on the walls of the tube that contains it. So it's bulk fluid pressure. And to continue with my hose analogy, because hoses are intuitive for most people, if I take a hose and I put one of those nozzles on and then I turn it on, you know, nothing's going to happen. But then if I poke small holes in the hose, water's going to come out the holes, right? So this is analogous to what happens with capillary hydrostatic pressure. So small solutes are going to pass with water, because water forms hydration shells around solutes, through little tiny gaps. Anything larger is going to remain. So big things should stay in your blood. So for example, large blood proteins, carrier proteins, cells should not be squeezing through here unless they're white blood cells and they're there for a reason. So red blood cells, other stuff, those should be staying inside of the capillary, including platelets. So only very tiny things should be leaving. So because water is leaving, that means that the further you get along the capillary bed, the less the water in the capillary bed is pushing on the tube. So as you get bulk fluid exit, you go from quite a bit of pressure, so 35 millimeters of mercury worth of pushing on the tube, to only about 18. So one of the reasons that this keeps working is that the interstitial hydrostatic pressure, so the pressure pushing back on the tube from the interstitial fluid, is under ordinary circumstances at or near 0. So it's nothing. So even though 35 and 18 are relatively small, they're still bigger than 0, which means that the driving force is still going to be for fluid to leave the capillary. Okay, so reabsorption. This is challenging because we're thinking about different driving forces. So you diffuse a lot of water and ions out at the capillary bed. You get 85 or so % of it back at the venous end of the capillary bed, which is good because otherwise you would just be hemorrhaging water into your tissues and not getting it back into your blood. So you would have peripheral edema and low blood pressure. So you need this driving force to get water back. So why does the water come back? This is the tricky part. And this is because of blood colloid osmotic pressure. So for this part, I'm going to stop and I'm going to draw this out on the Epic Pen blackboard because yes, the numbers here are nice, but it's easier to understand if you have a picture to look at that's sort of dynamic in nature. So I'll draw it. And to do that, I'm going to use my pen. So give me a second to get situated here. Also, I'm going to try and keep the chat up, but usually when I take my screen off and do this, it makes the chat go away. So just FYI, I'm going to talk through this. I might not be able to see any questions that come up while I do, but I'll address them when we come back from the screen share blackboard if possible. Ooh, this is exciting. All right. So let's go to Blackboard. Oh, look, the chat stayed. Hooray! Okay, so let me draw myself a capillary bed real quick. And I'm going to make a really, really simple capillary bed. It's going to have one capillary in it, just because I don't want to spend a lot of time drawing a million things. What's my dot size at? Okay, that's good. I'm also going to make things pretty wide so that I have enough room to draw particles. All right, so let me get my, and then I want a middle part that's like purplish. And then let's do the venous end, which is blue. Okay, so I would be a bad scientist if I didn't label things. So let's arterial. And I'm going to make myself a key here. So okay, so my particles are as follows. There's water, red blood cells, albumins, and fibrinogen. I'm not going to draw all the individual ions. We're going to assume that the ions are leaving the capillary with the water. So let's also draw our pressures. So over here at the arterial end, we have 35 millimeters of mercury. And over here we have So I'm going to be quiet for a moment while I draw, but what you're going to see is I'm going to have different stuff on the left side than I do on the right side. Okay. So over here at the arterial end, we've got hydrostatic pressure in the amount of 35 millimeters of mercury. So what that means is, due to that hydrostatic pressure, water, along with solutes, are going to leave. So over at this one, I'm going to write H2O leaves because blood hydrostatic pressure is greater than interstitial hydrostatic pressure. Oops, why did I make that an R? P, there we go. So notice in the picture, in the middle of the capillary bed here, let me add some more water on this end. So as the water leaves, we get concentration gradient happening, where in this part of the tube, the osmolarity on the inside and on the outside of the vessel are different. So I'm going to ask you guys this question, and I'll have you answer. I'm going to call this area of the tube area A, and this area of the tube area B. Which area of the capillary do you think has higher osmolarity? Remember, osmolarity is just the total amount of dissolved solutes in a solution. So who has higher osmolarity, A or B? Not quite. So remember, osmolarity is number of dissolved solutes compared with water. So look at the number of blue dots in B. Exactly, B. So the osmolarity of B is higher because there are more dissolved solutes and less water. So in B, we've got so that change in osmolarity means something. So I'm going to go away from my capillary bed, and I'm going to give you guys an example down here on the right-hand side. So let's say I have a cell, and the osmolarity inside of the cell is 300 milliosmoles, and the osmolarity outside of the cell is 1 milliosmol. Is water going to enter or leave this cell? Keep in mind the rule of osmosis is that water follows solutes. The answer is water is going to enter the cell. So remember, this was that tonicity lesson that we had in 160. And I bet you in 160 you were like, when am I ever going to use this? Ha, you are now. So if the osmolarity is greater on one side of a thing than another, for example, on one side of a cell membrane or on one side of a blood vessel, water is going to move in. So oops, I wanted to erase the white part, not the pink part. There we go. So if I were to make a chart that measured the osmolarity from side A to side B, I'm running out of colors. Let me switch to orange. It would look like that. Where it's relatively low at the arterial end. And then as water leaves due to hydrostatic pressure, we get water re-entering. And by the time we get to the venous end, about 85% of that water that we lost at the arterial end has come back in. So yes, water goes back into the venous end, not because of hydrostatic pressure differences, but because of osmolarity differences. So basically, we have two different forces driving water movement: hydrostatic pressure at the arterial end and osmolarity, so colloid osmotic pressure at the venous end. And that accounts for about 80% of water reclamation. And so at this end, H2O enters because blood colloid osmotic pressure is greater than interstitial colloid osmotic pressure. So that's our little water loop. So at the capillary bed, you can think of water as being kind of like a boomerang, where it gets thrown out, and then most of the time it comes back. Now, where does that remaining water go? So we've got about 85%. And apparently now I've lost the ability to draw a percent sign. Great. So about 85% of the water that was lost is gained back at the venous end. So where does the rest go? Well, it goes into lymphatic vessels. I momentarily lost my thing for some reason. All right. And lymphatic vessels have valves, so I'm going to draw that. So about 15% of the water ends up in the lymphatic vessel, and that's how your lymph is formed. So I'm going to take a screenshot of this so that you can look at it. Obviously, if you just looked at this picture and had never heard what I was just talking about, it might not make a whole lot of sense to you, but for those of you who are here, it will. And then we'll go back to the PowerPoint and look at the numbers as well. Okay, so what are the exact numbers? Well, it turns out the blood colloid osmotic pressure is about 25 millimeters of mercury. And yes, colloid osmotic pressure is measured in millimeters of mercury as well. Sorry, hold on. I'm putting my computer back together. There we go. Oh, that's a fun, weird little stretch thing. Look at all the videos I've produced. Go away. There we go. Okay. So get rid of that. So water re-enters because ICOP is 0. Blood colloid osmotic pressure due to water leaving and solute staying inside is 25. So that's the deal there. So I just drew out for you how and why that is. Now let's look at the numbers. And hold on, I'm gonna try and get my chat back if I can. I just lost you guys, so I'm grabbing you again. Come back here. Okay. There we go. Now hopefully you will stay put if I swap. There we go. Cool. Okay. So filtration is the word we use when we want to describe water leaving due to hydrostatic pressure. And notice that interstitial colloid osmotic pressure and interstitial hydrostatic pressure are both 0. This is in a normal, healthy person. So this is assuming someone doesn't have various problems like edema or plasma proteins issues, etc. So as we mentioned, capillary hydrostatic pressure varies from 35 at the arterial end to about 18 at the venous end. Blood colloid osmotic pressure, due to the water leaving, ends up being around 25 millimeters of mercury, but it's 0 in the interstitial space, so water goes back in. So Starling's law of the capillaries is just that reabsorption almost equals filtration. And that's that 85% thing I was talking about. So about 85% of what is lost is gained back. So net filtration pressure, net meaning gains plus losses, right? So if you're looking at like your net paycheck amount versus your gross, the net is after some math has been done to it to take money away from you in the form of taxes. So net is a subtraction function here. So this is net hydrostatic pressure minus net colloid pressure. Fortunately, the math on this is usually pretty easy because usually IHP, let me grab my laser pointer. So usually IHP and ICOP are 0. So what that does is reduces this math to hydrostatic pressure minus blood colloid osmotic pressure, unless something weird is going on. So here's a similar picture to the one that I drew, but this one doesn't give you a bunch of dots to look at, so you can't really, you don't get to think about the relative amounts of water versus not water as well. So I like to do both so that people that are more sort of drawing forward can have their little thing that they learn from, and then other people can just use this. So if you look at the numbers here, 35 out and 25 in at the arterial end means that the net filtration pressure here is plus 10. So plus means fluids leaving. In the middle, we've got this small area in the center of the capillary bed where there is no net fluid movement because they're about equal. But let me ask you this. If this were a cell membrane and there were 25 millimeters of mercury on each side, what would we call that? Anyone? What happens when both sides of the membrane have the same amount of stuff on them? That's called equilibrium. No change, correct. So the name for it is equilibrium, meaning that there's the same stuff on each side of a membrane. And as person in the chat whose name I almost said, oh my gosh, near miss, as that person said, that results in no change, so no net movement. What we taught you in Biology 160 is that diffusion forces, so movement, stops when equilibrium is reached. So let me ask you this. Why doesn't exchange between the capillary and the surrounding fluid, why doesn't it stop here? Why does it keep exchanging? Why do we get reabsorption at all if we've reached equilibrium at this point in the middle? So look at the picture for a moment and think about that. Anyone? Here's why. Even though we have diffusion forces, which are such that there's no net movement here, keep in mind, the heart's pumping. So bulk fluid movement, blood, is flowing through this. So the bulk fluid movement is what keeps the diffusion going, even though in the middle here we've reached equilibrium. So again, this is why having blood actively flowing is important. If you don't, this system would reach equilibrium very quickly and you would get stagnation, and stagnation equals death. So this is why stoppage of blood flow is bad. And this doesn't have to mean death of the entire body. Imagine if this arterial got blocked by, say, a traveling arterial plaque. This system would reach equilibrium, exchange would stop, and the tissue around this capillary bed would die. So if that tissue were, say, in the myocardium of the heart, that would be a myocardial infarction or a heart attack, and you would get localized tissue death. Or if it was in the brain, you'd get neuron death. Or if it was somewhere else, you'd get ischemia causing tissue death. So keeping fluid moving through the capillaries is key to health of the surrounding tissues. We don't want to actually reach and stay at equilibrium ever. That's bad. Okay, so summary. Fluid exits the arterial half due to hydrostatic pressure, so the force of fluid pushing on the walls of the vessel. Fluid enters the venous half due to colloid osmotic pressure, and actually the primary driver of this is albumins. So I included fibrinogen and red blood cells and other things in my drawing, and they do contribute, but the big player here is albumins, and that's also because albumins are the most numerous of your blood plasma proteins. And then you get this net loss of about 3 milliliters per minute, but that goes into the lymph. So what that means is, assuming a normal, healthy cardiovascular system, over 24 hours, you get about 24 liters filtered and only about 20.4 reabsorbed. Those are returned, of course, by your lymphatic system. So continuous movement is key here, and that is why the heart is so important. Okay, so it's now 11:24. It seems like a good time for a short break. So I'm gonna go use the restroom and grab another cup of coffee, and then I'll meet you back here in about 3 minutes, and we will try and finish the blood vessel PowerPoint.